Last time we started with the topic of method development in liquid chromatography, and we don't have the screen switched on, yeah? So let's switch it on also. Okay, but before we continue there, then we also had one thing to think at home. And this was this 2 lectures or 3 lectures ago, this work. So we already discussed that what chromatography type it could be and what causes peak width to grow over time. And then here, this higher eluent flow rate. This was the question, whether this would yield similar result as eluent with stronger organic modifier. So the question was, how do we know, or is there any way to know which one was the case? So to what conclusion did you arrive?
There was no way.
There is no way? Okay, how do you know?
Like the previous time that I have worked with that, it always tells you in the specifications, like with a gradient dilution or something like that, and constant flow rate. Like most of the time, it's a constant flow rate, and the easiest thing to change is the composition of the mobile phase.
Okay, yes, that's true, and indeed, in methods, nobody changes the flow rate during the run, especially, and usually one single constant flow rate is used pretty much always. Well, if the column dimensions are the same. So this is also. But in this theoretical study, as we are here at the moment, then we should consider also both possibilities, that flow rate is different and that the percentage of organic modifier is higher. So I collected this kind of information here. So in the left-hand column, we have 3 chromatograms with differing percentage of organic modifier. So indeed, the retention times get lower, retention times get shorter when the percentage is higher, but we see that they tend to stay to some limiting value. They cannot be too short. Can you tell me what this limiting value is? Sorry?
The L1, like when the mobile phase, it's the one that
elutes the fastest, and this is the dead time or the void time. So indeed, the shortest possible retention time we can obtain this way is the void time or the dead time. So it will, what's the mathematical term? It will approach this value. In case of flow rate, the mathematical relationship is this main equation of elution that we had in the first lecture. And although the flow rate is not directly shown in the equation, then this Tm, this depends on the flow rate. So if we increase flow rate 2 times, so the eluent flows 2 times faster, then the Tm is 2 times smaller. If we would increase the eluent flow rate 100 times, then Tm would be 100 times shorter, and so on. And this would reach, theoretically, of course, not in practice, theoretically, it could lead us to the 0 retention time. In case of infinite flow rate, the Tm would be 0, approaching 0. So, in conclusion, as the question was, is it flow rate because of flow rate change, or is it because of %B change? Then the relationships are different. In one case, it depends in a, let's say, mechanical way on the flow rate. In another case, it depends on %B, and it approaches the Tm, the dead time. And yeah, could we tell from just 2 chromatograms which way it is, as was our exercise? Just those 2 chromatograms? Well, not easy. Not easy to tell from 2. If it was 3, then yes. From 3 chromatograms, we could tell which one it is, whether this case or that case. In this case, we see that linearly the retention time gets shorter. So 2 times shorter in this case. It's above 40 or slightly, above 20 slightly, and once again 2 times faster flow rate, and it's slightly above 10. Here we see that, let's take this one, 40 minutes, a bit above 20 minutes. It could continue to above 10 minutes, but we see that it's approximately 15 minutes. So it's not linearly correlated anymore. Okay, so not easy, but possible. Anyway, in your answer, it would be great if you discuss both cases. So in a very full and long answer, as the exercise was here, what change resulted in the chromatogram number 2, then you could have listed what factors could affect retention times and say that, okay, it could be the eluent flow rate, it could be %B, the dependencies are this and that, and so on. Of course, the time given for this exercise was so short that I can't expect you to write it all, but in long case, yes. Okay, and so on the last slide, I also listed the experimental conditions which actually were used to record those chromatograms. So we already had this chromatogram and this one, but new information is that %B was 60% here, 70% here. So the methanol content of this eluent was 10% higher. And flow rate was 0.2 milliliters per minute, so quite low flow rate. Okay, I hope we can now finish with this one. By the way, I think I replied to all those also who sent this solution to this exercise by email. If I didn't reply you, then please send it once again. So I missed it somewhere, but at least according to my notes, I have replied all of them. And on the paper, I have Hamdi, and he Hamdi is here, indeed. Okay, so 2 more are here. All right, but then let's continue to method development slides. And we reached to some point already, so we had a look at method development steps. So first one has to define the goals, exactly what compound are we going to analyze, what exact compound and what is the task. Is it to separate some isomers or just to quantitate it from the sample? Then we have to gather information about analytes, especially if it's acidic or basic. What is the pKa value? Then about sample, it requires very different sample preparation. For example, either we analyze some pharmaceutical ingredient in pharmaceutical formulation or in some environmental sample, for example, in drinking water. So very different approaches. Then we need to obtain initial chromatograms with some relatively, let's say, general method. So initial chromatogram, and in this part of the lecture we use reversed phase chromatography detector. We don't focus on this at the moment, so it can be any of those. And after obtaining the initial chromatogram, we need to optimize the method. And mostly what we need to check is resolution and peak asymmetry. So if the peaks are very asymmetric, then we have to deal with this and somehow try to get symmetrical peaks. But we focus on peak resolution, so how to obtain good separation of neighboring peaks. And as we saw last time, then the peak resolution equation can be developed into this form, where we have 3 separate terms: retention term, selectivity term, and efficiency term. And we already started discussing this, that this retention, most of all, we need to adjust conditions such that the retention factor, this K value, is in between 2 to 10. Well, in complex cases also from in between 1 to 20 is acceptable, but let's focus to this 2 to 10 range. And why is it important to focus on this range? Because in this range it's very sensitive, or let's say it contributes a lot to the separation. So relatively small change in K value, well, from 1 to 3, so just 2 units higher. And this peak separation increases 1.5 times, so 50% higher RS value. And just for comparison, in later times, the change in K by 10 units gives us only 5% of increase, not 50% anymore. And as a penalty, the retention time is 2 times longer, which is probably just too much. So we try to adjust the K value to the range from 2 to 10. Now, how to optimize this? We changed the percentage of organic modifier or organic component of the eluent. And this slide says that we start from high percentage of organic, so let's say 90% of methanol or 90% of acetonitrile, then 80 and 70 and 60. Why don't we go the other way around? Start from, let's say, 10% organic, then 20, and then 30 to save time. How does it help to save time? The same steps.
If you increase the concentration of strong element, it will be like less time. But if it's like just 10%, you're gonna wait for a long time to like some components to use. Okay. Yes.
But I think if we put like the strong first, it will wash everything. So we need like to, or this is not something else.
No, this yeah, it's still this strong eluent component, yes.
Yeah, wash like everything with the strong thing. It will not make separation at the end.
Okay, there is no separation, but this is bad then, isn't it?
No, like if we start by 90% strong.
90% strong, so no separation, everything elutes fast. Is it good or bad?
It's good, I think, because then if you go to 90 and 80, then you don't need the peaks to be like so much apart, or a little bit apart. So
it's bad in the beginning, but if you're optimized, because you're not gonna have like peaks separated, but if you like notice that, you will save time. Like my classmate was saying, it's better optimize from having overlapping all the peaks instead of waiting that with a high percentage of strong eluent until all your compounds elute.
Indeed. So if we go this way, as said on the slide, start from 90% of organic component of eluent, then very likely that when it's 90, then everything elutes fast. We don't see any separation. But at least we know that everything is out of the column. And we get to know this very fast in short time. Then we elute with 80. Quite likely most compounds elute also very fast. Maybe some separation already starts to appear. But still we can see that, okay, we have 4 peaks, maybe 5 peaks, and we know that pretty much everything is out of the column. And so on. The peaks in every injection, the peaks get long, the retention times get longer. We already start to see where they are. If we would start from the other end, from let's say 10 or 20% of organic, then we make the injection, we may wait for 2 hours and still wonder, did every compound come out already? We still don't know. So yes, it's better to start from high organic side.
So like the organic eluent here is just strong one?
Yes.
Okay.
Yes. Yes, starting from the strong, high percentage of strong eluent component. Okay, and as I mentioned also last time, that the relationship between logarithm k and the percent b is more or less linear. And to draw a straight line, we actually need just 2 points. So if we have just one analyte, then in principle, to draw this kind of line, we need to just make 2 measurements. We may make one measurement at 50%, another measurement at 70%, and then already draw the line and start to estimate what percentage could be appropriate, or which percentage is suitable, so that we don't need to make all the measurements at 10% intervals. We may already go faster, and even faster if we take the approximation that this S is around 3. We will see in one example how much 3 it is or isn't, but we will see. Okay, then if we have several analytes, then we can optimize the %B for several analytes. And for example, in this case, okay, I don't tell anything. Instead, I ask, how is this, or what does this green area note here?
Area where the key values are suitable from 1 to 10. No, from 2 to 10.
Okay, how do you know?
Because of the lowering, like it's 3 points. Lowering from 0.3 must be approximately something like 2 or something. Like between those range.
Logarithm of 2 is equal to 0.3 indeed. So this gives us the lower range, and the upper one is logarithm of 10 is is 1. So it's drawn a bit above 1, but yeah, it's meant to be 1. Okay, so indeed, and the things, or the values, or %B values which remain for all compounds in this range, those should be suitable. For example, this 50, let's say 7% is suitable because for all 3 compounds, the K value is in between 2 to 10. So we see it here. But we also see that for 2 peaks, the K values are overlapping, which means they have equal retention times, which means they are not separated. So if we choose another percentage, maybe 70%, then we see that still all the compounds have suitable retention factors, still between 2 and 10. But it's very likely that they are nicely separated. So according to this graph. So this graph and this relationship allows us to optimize not only the retention time or the %B, but also the separation. So we can see both. Now it comes to selectivity term. So the second term in the peak resolution equation. And similar graph here, we see that if the selectivity is somewhere, let's say, from 2 to 6, 7. So then changing it or gaining more selectivity gives us quite a lot of change in peak separation. If we try to gain higher selectivity, let's say from 10 to 15, then the gain is practically non-existent. So it's worth trying to get bigger selectivity in this range if the selectivity is from 3 to 7, or in this range, then increasing the selectivity gives us more peak resolution. Okay, but how to increase selectivity? And here, the most influential parameter that we can change is pH. So small change in pH may very much affect the retention time of a compound. And if one of the compounds is, let's say, acidic, another one is non-ionizable, then one retention time is easily affected by pH and another is not. And therefore, we can affect the selectivity. Then second, solvent type also affects selectivity. Methanol, acetonitrile, THF. We can combine them or use one of them, and one or another gives different selectivity. Those first two are relatively easy to change. So we just prepare or use different mobile phase components, and that's it. Stationary phase is not that easy to change. We need to have different column. So buying a different column is quite expensive, and if we don't have it already, then it takes time until it's delivered to the laboratory. So not that convenient, but definitely can help to increase the selectivity. Ion pairing reagent, possible. It's in brackets because in case of LCMS analysis, we would try to avoid ion pairing reagent. But in general case, if we consider liquid chromatography in general, then ion pairing reagent is a good way of altering the selectivity. Then %B can alter selectivity, and we will see this also. We already actually saw it on previous slide. And temperature, well, in general has very little influence. There may be some cases where it has more influence, but in general, very, very small influence, and therefore, usually we don't play around with temperature for selectivity. Okay, one example about the influence of pH. I think you have seen so many examples already that perhaps fed up of this. But once again, showing a demonstration where pH difference by just 0.1 units gives us good separation. So resolution is 3.0, which is very good by all the validation guidelines and requirements. And at pH 2.2, the separation between those two peaks would be not sufficient. So very small difference in pH and different retention time. Well, good example in the sense that how sensitive the separation can be towards pH. But I would say it's a bad chromatographic method. It's not robust. If so small pH variation causes big difference in retention time, then it's not a robust method, robust LC method, LC separation. So most likely the pH, this 2.2, 2.3 is very close to the analyte's pKa value. This is where the effect is the strongest. And this is a bad way of designing methods. pH of an eluent should be at least 1 pH unit away from all the pKa values of analytes. So the further the better, but 1 unit at least. So yeah, once again, nice to remind how important pH is, but also nice to remind that keep the method robust. Okay, and those curves again, that if the compound is acidic, is a weak acid, then its retention time is longer at low mobile phase pH values. Retention time of basic compounds is longer at high pH values, and neutral analytes don't care about pH. Okay, some buffer solutions used in liquid chromatography to control pH. So phosphate buffer for all those phosphorus acid deprotonation or deprotonation stages. The red numbers in this table refer to those pH values which are very likely not suitable for column. So pH 1 is too acidic for silica-based column, and pH 11, even pH 9 is too high for silica-based columns. So those should be avoided in usual columns. So there are some special columns which tolerate pH values outside those ranges, but in general, no. And concerning liquid chromatography with mass spectrometric detection, then the buffer solution must be, or buffer components must be volatile. Phosphate is not volatile, therefore not suitable for LCMS. Acetate, formic acid, ammonium formiate, those are volatile, therefore suitable for LCMS analysis. So is this the full list of buffers? No, it's just the most common ones. So there can be more. Once again, pH, how important it is and what happens to retention times of compounds when pH is altered. So indeed, I think it's already a lot that we have stressed this. Okay, then the second factor that can be used to alter selectivity was solvent type. So if we change the organic component or the strong eluent component, then we may change the retention order, the retention time and peak order. So both may change. And acidity, basicity, polarity of solvents all play a role. So those are, let's say, the factors that we have to consider for separation of compounds and dilution of compounds, but we also have to keep in mind the detector. So if it's UV detection, then the detector or the eluent should not absorb in the range where analyte is expected to absorb. So we have to consider also the UV absorbance of eluent. Then column back pressure. So if the eluent is really viscous, then the back pressure is so high that we just cannot pump it through the column. Then some eluent components may be available, just that the purity is not high enough. So we need to change and keep in mind that the eluent purity is important. And also the eluent stability or the eluent system stability, there are different possibilities what can happen to eluents. Yes?
On the previous slide, is there a theory to understand this, or is it just trial and error?
Yes, there is. It's still the same that we had here, that if we have acidic analyte, then if the pH is low, it means it's acidic, then the acid is protonated, and when protonated, then it's less polar, so its retention time is longer in reversed phase column. And this is exactly what happens here. So the acids are shown in red, and if the pH is low, then for those acids, the retention time is longer.
If you are separating, like, let's say, same kind of acid, like fatty acid, for example, seaweed.
Sorry?
Like, let's say we are analyzing like the same set of acids, fatty acid, some kind of like.
Okay, yes.
Seaweed.
Then still the same applies. In case of fatty acids, where if the tail, which is hydrophobic tail, is really long, and there is a hydrophilic head, and pKa values of those long acids, fatty acids, are very similar. So just by changing the pH of the eluent, we cannot achieve much of selectivity, just because the pKa's are so similar. And the tail is very hydrophobic. Yep.
Now that I see, in the last slide,
This one?
no, like the graph with this one. Like, I understand why changing the pH affects a lot the bases and the acids, but I have a question, like, without information, why the pH doesn't affect, like, as much as as it affects to the base, like from the retention time? Because when you have
okay, so why does it increase so long here and
decrease with the same intensity?
So why isn't it, let's say, symmetrical?
Yeah, something. Yeah, why is the effect so noticeable with the bases?
Well, good question. I don't have answer to this. And I'm not even sure how it would look like experimentally. Does it hold experimentally exactly the same way? Oof. Okay, I will think of it and try to find something, but I even don't know where to look for. So let's see. At least I know the question. Okay, so where did we stop? Here. So solvent type. So there are many factors to consider when choosing the organic component or the strong eluent component. And let's have a look at one example. So we have separation of same 6 analytes. And in case of methanol, the optimal separation was found. It was found at 48% methanol. And we see that all 6 compounds are separated from 1 to 6. So the longest retention time is here, let's say 11 minutes approximately. The numbers are not very well shown, but approximately 11 minutes. So now if we switch to acetonitrile, then the concentration of acetonitrile is lower. And this is quite common that acetonitrile is a strong eluent component. Therefore, to achieve similar retention times, then the percent of acetonitrile required is smaller. Retention times, and now I think the retention times are just a few minutes here. I think it was 1 minute and 2 minutes here. So I'm quite sure it wasn't 20 minutes. Okay, so, but what we see is that peaks 1 and 3 are overlapping. Not 1 and 2, but peaks 1 and 3 are overlapping. Meaning that not only got the retention times very much shorter, but also the order in which the peaks elute from the column are different now. So 1 and 3 elute first, then comes this compound number 2, and then 4, 5, 6. And if we change to THF, then we see that it's even more different. Now the retention times are 8 minutes for the last peak. And the peak elution order is 1, 2, 3. So the beginning is the same as with methanol, but then it comes 5, 6, 4. So the compounds have changed their places. So the retention times are different and peak order is different. And if peak order is different, then this is the manifestation of different selectivity. So this selectivity was altered by using different strong eluent component. Yes?
Was it related to because it's basically the reaction of polar or non-polar solvents or something? So it's maybe the reason is the interaction of like the polar solvents that we are using?
Mm-hmm. It cannot be just polar, non-polar with one single parameter, because if this would be the case, then the retention times would get just shorter or longer, but the order would not change. So there has to be more parameters, and those are the parameters that are explained or currently taken into use. So basic acidic properties of solvents and also polarity. So three characteristics. And in principle, amines would be example of basic compounds. Then carboxylic acid would be acidic compounds or acidic solvents. And chlorinated solvents could be the examples of polar compounds, which are neither acidic nor basic. But those, for different reasons, are not very common or are not used as eluents. And in fact, the eluents that are commonly used, THF, alcohols, including methanol, and then nitriles as acetonitrile is here. So dipolar and, well, acidic, basic to very limited extent. THF in the halfway between dipolar and basic, but acidity is very low. And alcohols, very slightly acidic, and dipolar basicity is, well, relatively low. So this is mostly the range that liquid chromatography is operating. There can be a bit more compounds, but this is the most common range that is used. Okay, but even this range is quite a lot of possibilities. So, 3 solvents. Let's take those: acetonitrile, methanol, THF. And we can mix them to achieve suitable selectivity. So not only mixture with water, but also mixture of, let's say, methanol and acetonitrile plus water. So as was shown a couple of slides ago, then the eluting power of different organic solvents, of the different those strong components, is different. And we saw that 48% of methanol was used, so nearly 50% methanol was used. Sorry, methanol is here. So practically 50% methanol, and this corresponded more or less to acetonitrile percentage of 42, if I remember correctly. So let's see, where is, yeah. Oh, it was approximately here, this line. So for methanol water, it was 48 roughly. For acetonitrile, then it's around 40. And for THF water, it could be somewhere around 30. So considerably lower percentage of organic eluent. Yes?
I don't understand, like, is it like 40% acetonitrile equals to 50% like methanol, or how does that sound?
40% acetonitrile gives approximately the same retention as 50% methanol. And this in turn gives equal retention to 30% of THF.
So like the strongest here is THF.
Yes. Mm-hmm. And yes, this kind of nomograph is used to, for example, if we have optimized the separation with methanol to, let's say, 80%, and then want to try how does it work with acetonitrile, then from here we see that we should use approximately 70% of acetonitrile, or if we wish to test with THF, then roughly 54% of THF. Yes?
Is it always the case?
Very approximately. It's really a rule of thumb. So very, very approximately, it's just to start somewhere, and not to start from 90% again, just to get straight to the right direction.
It's the thing when we are carrying out the measurements, and I say, like, I want to change the solvent, the element. I have an idea, like, oh, I really like my retention time that I used to have before. So if I change to THF, I'm going to use this proportion, no?
Mm-hmm. Yes. For example, if we are working with acetonitrile, if we start with acetonitrile, we try our best and we see that, okay, still 2 peaks are overlapping. So we should try with methanol, and we check this graph and see that, okay, starting point should be somewhere around 50% methanol, and we test and we see that, okay, yes, it works, roughly. So not testing 40% methanol, but straight to 50 as required. Okay, and now the long way, or not the long way, but the systematic way. So this is just one possible method how to optimize selectivity. It's called Snyder method because it's described by this Snyder, this author, and it's also described in this textbook that I showed last time. So, methanol, acetonitrile, THF. Let's start with methanol. We take methanol, optimize the separation of compounds in a way that all the compounds elute with K from 2 to 5. We see that the last peak has a shoulder, so most likely there is some other component, and indeed our aim is to analyze 5 compounds, but we only have 4 peaks, so we didn't achieve the separation. Then we switch to acetonitrile, and we see that with acetonitrile, all the Ks are in between 2 and 10, but we see 1, 2, 3, 4 peaks, and two of them are partly overlapping and one has shoulder, so again, no good separation. Let's try with THF. With THF, we see 4 peaks, and one of them is with shoulder, so again, not successful. But what we notice from here is that those problems occur with different compounds. So here it seems that, here with methanol, we see that this last eluting compounds are probably overlapping, but with THF, there is no such problem. So if we could use something in between methanol and THF, then there are chances that we achieve separation. So let's mix now methanol containing mobile phase and THF containing mobile phase in 1-to-1 ratio. So for example, if here we found that 48% methanol is suitable, and here we found that 24% THF is suitable, then we mix those eluents in 1-to-1 ratio. And now we obtain this chromatogram, and we see nicely separated 5 peaks. Yes, we achieved the goal. Now the peaks are separated. In principle, we could stop here, but textbook continued, tried also methanol-based and acetonitrile-based eluent mixing. So if mixed, then still we see that there are 2 regions of overlap. Number 6, well, shows nicely 4 peaks. Unfortunately, we have 5 compounds, so somewhere there is an overlap. And number 7 in the middle means all the eluents in 1-to-1-to-1 ratio. So 1-1-1, methanol, THF, and acetonitrile-based eluent. And the result is here in the middle, well, not successful this time. So, yeah, this is the systematic way of testing and trying to achieve the selectivity. Yeah. Because we want to develop the isocratic method. Yes, at the moment we are dealing purely with isocratic, so no gradient. And of course, nowadays most of the laboratories have chromatographic systems which are capable of gradient elution. But yeah, those principles were developed when those gradient systems were not available. They were mostly built in the lab and were not easily reproducible. This is our next topic. So then we speak in which cases gradient is justified and needed, and also a bit about its optimization of gradient methods. Okay. Yes.
You were mentioning, for example, in the first chromatogram that using methanol, the method was already optimized because the key values were between 2 and 10. But like key value is considering one peak and the dead time. So here we are seeing that it's an overlapping peak. So it's a problem. Like which peak you determine that it was a correct value, a correct key value.
Okay, so those K values for all the compounds should be within the range of 2 to 10.
For example, in the last one, it's one overlap peak.
Yes, there is overlapping one. We just know that the compound is there. And we know that approximately its K value is, let's say, around 10. And that's it. We don't need more. We know that we don't succeed in separating it because it just coalutes with the other compound. But we know that K value is below 10 or approximately 10, and let it be. Let's test acetonitrile now.
Okay. And all the peaks must apply with the a value of a
yes,
K value.
Yes. K from 2 to 10 or 1 to 20 if it's very, very complicated case. Okay, now the next possibility to change the selectivity is to alter stationary phase. We can alter the particles, the core particles. It can be silica-based, aluminum oxide-based, or polymeric. Bonded phases or the stationary phases may be changed. C18 is the standard one. C18 has, let's say, a bit more polar nature. So C18 has less polar nature. Phenyl columns have, again, different selectivity, especially towards compounds with aromatic moieties. Cyana columns are quite polar, and therefore their selectivity is very different. So cyana columns are quite at borderline between reversed phase and normal phase. They in principle can be used for both. Okay. Now, one more note here is that if we say that the stationary phase is C18, then it doesn't fully determine the column properties or fully say that all C18 columns are equal. Two C18 columns from different manufacturer or even from the same manufacturer can perform differently. So the C18 columns can have different selectivities. And there are comparisons available which compare the columns. And Well, for some reason, companies keep moving their column information around. I'm not quite sure that the tools are still there at those addresses, but we will see one table about column properties. Yeah, let's do it right now. So let's share screen. And I upload it just for the case as it's, no, not this one, this one. Because they are moving around their information. So column manufacturer called YMC, and their columns plus some columns from different manufacturers. And on the horizontal axis, we see its hydrophobicity, and on the vertical one, its hydrogen binding capacity. So let's not go into details how and what do they mean, just that hydrophobicity on the horizontal, hydrogen binding capacity on the vertical axis. And we see that they have quite different columns. Some are very strongly hydrophobic, others are less hydrophobic. Some are hydrogen binding with low hydrogen binding capacity and others high. So if we look at the column chemistry, then this C18 seems to be at the right-hand side, hydrophobic, quite understandably. And we see C8 at the left-hand side, less hydrophobic, quite clear. And then we see that up here, there are strange column names like hydrosphere, which is a column which has some hydrogen bonding capacity added to the stationary phase. So, yeah, even one single manufacturer, they produce different C18 columns. And at the moment, we focus on this, that they on purpose design them differently. Also, if you buy one column of the same name from the same brand, everything should be the same, then be prepared that it behaves differently. So especially columns from different batches, from the manufacturer's batches, then there are some variations possible. Okay, stationary phase, and one example here. Starting point in this case was C8 column. 5 compounds were separated, and well, we see that nice separation was achieved. Retention times from 3 to 7, almost 8 minutes. If we would use C18 column, then we see that the retention time for last eluting compound is much longer. So the mobile phase was adjusted such that the first peak is relatively the same retention time. So it's a bit below 3, but we see that the last peak is then 11 minutes. So quite expected if we increase the hydrophobicity. With cyano column, we see that the retention times are shorter. So the first diluting peak is again at nearly 3 minutes, but we see that it's the compound number 3, then comes compound number 1 and 5 and 4 and 2. So the order is completely mixed. With C4, we see that the retention times are shorter again. Well, the hydrophobicity decreases in this row, therefore it's quite expected that the retention time is shorter. And phenyl column again has alternate selectivity. We see that the peak order is 1, 3, 2, 4, 5. So 2 and 3 have changed their places. So yeah, the stationary phase differences. Okay, percent B. Before we continue, any questions about those stationary phases? Everything clear? Yes.
The last image, all of them are non-polar stationary phases. Like, can you say that?
We cannot exactly say that the cyana column is non-polar, but what we can say here is that it's used in reversed phase mode, in reversed phase chromatography. So that eluent is more polar than the stationary phase.
Okay, so all of them are used in reverse phase.
Yes.
But like, for example, in the exercise that you presented us, you can predict which was the order of the compounds that you were presenting us according to its polarity.
Mm-hmm.
But like with different columns, we can do that because in that exercise, I think that it was carbon 19. So now that the peaks are eluted in different order,
Mm-hmm.
can you predict according to the polarity of the compounds which is going to be eluting first or second?
In simple cases, yes. In cases like this, where we have ionizable groups and non-ionizable groups, and the structures are very different, then to put it very mildly, then it's difficult to tell the truth, not very likely.
It will not be like a rule of thumb? Like
No. So this would be really difficult. But in that case that we had for the exercise, it was just the homologous series, just additional 1 CH2 group, and in that case it's simple. And indeed we can then predict the retention order.
Most of the time, we are not like sure whether this is like all the ethers or homologous series. So we'll just like try and get the separation. Because for example, if these are the compounds,
yes,
you cannot like determine like, for example, if you're using C18 column, the interaction of all of them will be different.
Yes.
So you're not gonna get an idea which interaction is stronger than the other one.
Exactly. Yes. In case of those compounds, what we can, however, predict is how would pH of the eluent affect retention of those compounds 1, 2, 4, 5. So pH affects their retention, but not number 3. This will remain unchanged. Okay, now about the percent B, and example here shows those plots of percent B and logarithm K, as we saw already before. And this shows it for homologous series, so very similar compounds. And we see that the graphs are, well, quite nicely in line, so similar straight lines. So if, for example, we need to separate those compounds, which are reflected by those two lowermost lines, then we see that by changing percent B, we cannot improve the separation. No matter what percent B we use, those lower two compounds here will still elute very, very close to each other. So yes, the graph is still useful, but we just know that, okay, it's probably not possible. Now, if the compounds come from different classes, then the graphs can be rather different. And we see that the slopes are quite different, and therefore at this position, if the percent B is, I would say, 13%, then separation of those two compounds is not possible. But if we would take percent B of 20%, then we could separate those two compounds, but probably have difficulty here. So to also separate those, well, it's tough. We probably can't separate all the compounds at the same time. But this is also a good information. If we get the information that stop trying, you can't, then we stop trying and try something else. So in any case, this kind of graphs, percent B and logarithm K, are very useful. Okay. What we can do using this previous graph, we can calculate alpha value. K's are available from there. Based on K's, we can calculate alpha value and then see how it behaves, and then whether this percent B would give us successful separation or not. And it can be shown graphically, and one so-called resolution map is shown here. Ooh, this is now difficult to explain. Let's start from this one over here. And within this red rectangle, there seems to be one peak, but in fact there are two peaks overlapping, completely overlapping. And this corresponds to this composition of the eluent. So the eluent contained 40% of component B. So the strong eluent component was present at 40%. And as those two peaks were completely overlapping, then it means that their peak resolution was 0, therefore very low point here. Now, if we start increasing the percent B and reach, let's say, this point, it's probably 50%. Then here the chromatogram shows that the peaks are, well, to some extent separated, partly overlapping in the middle, but still separated. So it was possible to calculate the RS value, and this RS value at 50% was something like 1.2, I would guess here. Now, if we continue, I would say this is 57%, something like this here. Now we see that those two peaks are more or less separated, but we are starting to have overlap here in this range. And now we focus on those peaks. So we don't draw the RS value for those two anymore, but now for those. And this RS value is calculated for so-called critical pair. So those peaks, those two peaks, which are closest to each other, or which are for which the RS value is the lowest. Yeah.
You The last one.
So somewhere in between those two compositions, what happened is that those peaks are separated good enough, but bad separation appears here. And therefore, now this graph at point C depicts already separation or RS value for those peaks. These are good. We don't need to calculate for them anymore. We just focus on this. It's quite a tricky thing that we don't show on the graph. We don't show the RS value for specific compounds, but we show the RS value of the lowest in the chromatogram. Lowest RS value of the chromatogram. And those two compounds which give the lowest RS value, these are called the critical pair. So critical pair of peaks. Okay, so somewhere at 57%, what happened is that we have new pair of critical compounds. The separation is critical here, and we show this point on the graph. Now the percent B is increased further to something like 70% here. And now we see that those peaks, which were a bit overlapping already in the previous one, are now overlapping even more. Therefore, we see that this RS starts to decrease, and we have a point here. Okay, why is this graph useful? If we have a requirement, for example, requirement that for successful analysis, the peaks of analytes must be separated by at least RS 1.5. If this is the criterion, then this graph shows we can draw a line here. We can draw this 1.5 line. And we see that, okay, those points are above 1.5. And we can then choose the percent B, like 57%. And this gives us good enough separation for all the peaks, because we focused on the smallest RS value. Okay, any questions? This is a tricky way of presenting things, so feel free to ask. Okay, yes.
So the thing is, we do not go above the resolution of 1.5, because then like we get another critical pair.
It can increase above 1.5. Well, we can imagine that there is one compound less. Let's imagine that this middle compound is missing, not present in the mixture. In that case, this could be higher. It could be 2 even. But then at some later point, definitely peaks start overlapping, and then still we can choose which point we use. Yes, there was another question, right?
here in the peaks that were not resolved enough, why changing the percentage of the strong element is causing like them to not be overlapped anymore. If like we are just we are using the same element, like the same strong element, we are not changing between one element or another to like change the selectivity. Why it's like reducing the
Yes, I'm not sure if the question was heard. The question was why changing just the percent B, how this can change the peak separation or the selectivity. Then this is the answer here, that we see that at 13% of those two compounds are not separated, and at 20% they are. Although the compounds are the same, the element is the same. Just the proportion is different.
That graph, we can understand like each molecule interact differently, so we cannot like know like how the I mean like they're like interacting differently, so it's so hard to predict from like only
Yes. Yes. Only by looking at the structure of the molecule, it's very difficult to predict what would happen in reality. And if we consider that it is an interplay between stationary phase, which has more than one type of interactions, then mobile phase, which has two components, different characteristics, acidity, basicity, polarity. Then pH of the mobile phase. Then we have analyte, different pKa values, different polarities. So a very complex system. Yes, there was another question.
So it's not like C and D. We only like tried 1%. Like why didn't we try like between C and 60%?
Yes.
We didn't know that it would decrease.
Yes, it's possible to test other percentages also. And of course, if it would be a real development example, then one would definitely try to optimize it further, whether using, let's say, 50, 59 or 60%, whether this would give higher point here, maybe.
It might get
Yes, yes. Or maybe it gets down. We don't know exactly.
like we can only predict the retention times or like how it's gonna change when we have polar or non-polar like analytes or compounds where like just changing the percentage of the element will cause a reduction of the retention times. But for other cases, it's like creating these linear graphs experimentally. Like we're gonna have like this, the one that you showed me in the last slide. But for every compound, you need to do like this procedure experimentally.
Yes.
Okay.
Mm-hmm. Okay. Then percent B. Okay. Similar curves or similar plots like this one. The resolution maps can be created also for temperature of the column, solvent type, pH value, and so on. So we can do the same for different parameters and map the whole space. Okay, and finally the efficiency term, so the number of theoretical plates. The efficiency term, as we see it, has this square root mark. So if we increase efficiency 4 times, which is a lot, then we gain the peak resolution only 2 times. So that this efficiency term is difficult to get use to use this because we just need to increase it that much to get the better separation. Okay, if selectivity is okay, then we can, and still there is no separation, then we can try increasing the efficiency. So if the resolution is sufficient, for example, the peak resolution is 2.5, but we know that we need to analyze 2,000 samples, then we can make the method faster just by sacrificing the efficiency, the number of theoretical plates, and make the method faster. Okay, if we take a starting point, 15 centimeter long column, 4.6 internal diameter, this classical old-fashioned column with 5 micrometer particles. This kind of column has roughly 10,000 theoretical plates. So, eluent flow rate and particle size, those affect the efficiency via Van Dinter equation. Now, if we make the column 2 times longer, then we times plates. So, or if we make it 2 times shorter, then again we lose half of theoretical plates. So this doesn't directly come from Van Dinter plot, Van Dinter equation. Therefore, it's important to stress that this is also there. The column length plays also a role. Okay, Van Dinter plot. We will consider this in a minute, and columns with different particle sizes show different curves on the plot, and optimal flow rate. This depends on the particle size, and if we increase the flow rate too far, then or above the optimal flow rate, then the efficiency will get lower. Smaller particles would give higher number of theoretical plates, but cause higher back pressure. So we just physically cannot force the liquid through the packing with very small particle size. If the particle size is 10 micrometer, then the usual plot Van Dinter curve looks like this. 10 is the 5 micrometer particle size is the classical, so somewhere around 0.2 centimeters per second, the flow rate is the optimal. And if we have very small particle size, smaller than 2 micrometer, then increasing the flow rate above the optimal, well, it doesn't increase the plate height that much. We see that the increase of plate height at non-optimal flow rate is not bad for 1.9 micrometer particles, but it's very bad for 10 micrometer particles. So that with 1.9 micrometer particles, we can use higher flow rate without loss of efficiency. Okay, if we replace 15 centimeter column with 10 centimeter column, then we save 33% of time, and resolution decreases only by 6%. So if we can sacrifice this 6% of resolution, then that's fine. we can make the method faster. 33% faster is a lot. So that's the good point of using small particle columns, higher flow rates, and so on, and shorter columns. Okay, any questions?
Slide 21, can you ask about the acid and base?
Sorry, slide number 21.
Yes.
Oh, okay, let's go to slide number 21. And, okay.
I think in this resource, they mentioned that the acid and base, like there are specific examples, not like general rule, and they might depend on like how strong and weak the acid and bases are.
Ah, okay. So that you checked that this is described there, that this is for specific compounds. Yes. Okay, I see. So for specific compounds, it looks like this. In general, it may be different. Okay, that makes perfectly sense. Yes. Okay, thank you. Any further comments or questions? If not, then we are done for today. Thank you and see you on Wednesday.